The next topic we're briefly going to talk about is electric flux lines. So an electric flux line, or sometimes you'll also hear it called an electric line of force, is just an imaginary path that we draw to help us visualize the electric field. So these paths are drawn in such a way that the direction at any point is the direction of the electric field at that point. So to sort of get a better idea of this, we can think of our simplest case of a point charge. So if we have a point charge located at some point in space, then what we can say is it's going to have electric field lines, or electric flux lines I should say, that are pointing out in all directions radially. So remember, for our point charge, the only dependence is in the r direction, so our radial distance from the point charge. So we would have electric flux lines that look like this. And so now keep in mind there would also be lines coming into and out of the page at all angles, so it's basically a sphere of these electric flux lines sort of emanating from our point charge. And so let me go ahead and label that this is indeed a point charge that we're talking about here. Okay, so we have some point charge, and so let's label that as Q. So another important thing that we can talk about is with these sort of electric flux lines, we can also define something called equipotential surfaces. So as the name implies, these are going to be surfaces, again, not physical surfaces, but sort of imaginary mathematical structures along which our potential is equal. So let's come over here and add some dashed lines for our equipotential surface in this point charge system. So because it only depends on r, we're going to have circles around our Q, which is going to have, along that surface, going to have the same electric field, and therefore the same potential. So we can have multiple electric equipotential surfaces, and again, so we would define these. This is 2 dimensions, so it looks like circles, but keep in mind this is really like a sphere, which is a surface along which our potential is equal. So any point on that surface is going to have the same potential. So what that means is that moving along that surface, we're going to have no work done. So let's say moving, so no work done, moving a charge along one of these equipotential surfaces does not require any work. So equipotential surface. And so we can get that from our previous definition of work way back when we first introduced our electric potential. We said that our work is equal to our potential difference. So if we just say 2 arbitrary points, so for instance, maybe this is point 1 and this is point 2, it could be anywhere on that same surface, times the charge. So if we're trying to move some point charge Q along that surface, then that's going to be equal to 0 because this V12 is equal to 0. Because the difference of V1 minus V2 is equal to 0 because they're on that same equipotential surface. So another way that we could state this is we could use our expression related to electric field. So we could say the line integral of E dot dl along that equipotential surface is going to be equal to 0. And so what that means then is that our flux lines are always going to be normal to our equipotential surfaces. So our electric flux lines are always perpendicular or normal to those equipotential surfaces. And so we can see if I've done a good job drawing it up here for our point charge, but if we were to look at any one of these equipotential surfaces, we're saying it should be normal to all of our electric flux lines, or the electric flux lines passing through it. So all of these should be normal. So that one I drew a little poorly, but for the most part we see I didn't do too bad of a job drawing that. So of course a point charge is sort of the simplest case. Let's take a quick look at our electric dipole. So our electric dipole equation we just looked at in the previous video. So remember we had a component in our r direction where that is the distance from the center of our dipole, and we also had a theta component. So we had something in our theta direction where that theta is defined as the angle from the axis of our dipole. And so if we plot that, we end up getting something that looks like this. So definitely a lot more complicated, but a lot sort of prettier than what we have for our simple point charge. So this is just sort of manifested. We have our blue curves here, our flux lines, our electric flux lines to be exact. And then our dashed lines here are our equipotential surfaces. And so what we're seeing in those blue curves is we're seeing that R and that theta dependence. And if we, again, sort of zoom in closely, we can see if I've drawn this well, we should see that at any point, these electric flux lines are perpendicular to our equipotential surfaces. And so for the most part, we see I didn't do too bad of a job drawing that. And again, we can notice that there are directional arrows. So for instance, for this electric dipole, in the left side, we see that our directions are going along this path, sort of in a counterclockwise direction, whereas in the right, our direction is more, it is in the clockwise direction. And so these electric flux lines, again, are very useful for visualizing our fields. And one sort of interesting application is a lot of studies centered on hearts, in particular human hearts, will utilize flux lines and equipotential surfaces.